Today, chapter 14, next time, chapter 15. Once we're done with chapter 15, that's all the chapters that are going to make up exam number 1. So I would encourage you at that point to go ahead and take a look at the practice exam. I know you're, juggling a lot of things all at once, and, such is the life of college student. Oh no, I shrunk it when I meant to expand it. New share. So right now we're in week 2, July 20 and 22nd. Next week is week 3, July 27th and 29th. On the 27th, we'll be covering chapter 15 material. On the 29th, we'll have a quiz on chapter 15, and I'll field any questions you have, but it's also a really good time for you to have spent some time going through the practice exam. The practice exam for exam number 1 is 2 practice exams, because I used to divide this up into smaller pieces, and it didn't make a whole lot of sense, but I did it anyways. I will advise you to look at the questions and pretend that you are taking the exam. You will see the equations that you'll have, and then you will see a bunch of questions. Try to answer those questions without looking at the answers. The answers are there for you to see. See if you got them right, see if you understood it, or to hopefully explain to you how to get to the answer. And boy, this is just not spaced out well. But anyways, try to do it without looking at the answers first, because it is just very easy to convince yourself that you know how to answer a question when you look at the question and the answer together in one sitting. You just do yourself a much better service if you look first at the questions and then maybe take a look at the answer key. Oh, come on, go lower now. I have posted here the academic integrity regulations just as a reminder. When you're taking quizzes and exams the first time through, I'm saying that you can use your calculator and the equation sheet that I provide. I'm not doing some of the contortions that some of my colleagues have done with lockdown browsers or some kind of person to proctor your exam in a way that's maybe less comfortable. So we're doing an honor system here. It's my intent that you take it the first time. It's not super high stakes, because the first time you don't have those outside supports and you're just showing me what it is you know and can do and show your work, and I can give you partial credit. But you also have the second shot at it where it will keep your average score. And the second shot is open book, open notes, and hopefully things that you might have missed the first time will make more sense the second time. That is a week from Tuesday when we'll actually be taking exam 1. For now, we're still building up the material we need for that. So if you think of questions on chapter 13 homework, hold on to those for that time that we'll have at the end of class where I say, hey, do you have any questions before the quiz? And for right now, we're going to jump into chapter 14. I have to go back to the beginning, and I have to share it with you. Okay. When I made this PowerPoint, I put together some things from the previous chapter and some things from the next chapter, all in one PowerPoint. So there's some stuff at the beginning that I'm going to blaze through a little bit quickly, just because it's reviewing what we covered last time. And then there's some stuff at the end that I'm going to stop short on because it's actually stuff for a little bit later. So here we go. So last time we were talking about this kinetic theory of gases, that when you have gas molecules inside a finite sized container, and those gas molecules are behaving like ideal gases such that they don't condense into a liquid. On average, they're pretty far apart from each other. They're going at a random distribution of speeds. There's all sorts of information that's kind of embedded in that gives us access to a world where in statistics, there's often a distribution. Not, everything is exactly the same. There's a range of different possibilities. And so this world of statistical thermodynamics is on the plate here for us. And that means that there'll be a distribution of molecular speeds at any, what we would call temperature. So if you have a bunch of molecules that are all, we would say at 300 Kelvin, right around room temperature. The most probable speed for any particle in there is 400 meters per second, but there's a range. Some things are going wicked fast, some things are going kind of slow. And what we found is that if we build up from like very basic first principles, Newton's second law of force equals ma, therefore we have this relationship between force and momentum. And if we have this idea of momentum and the time between collisions, we could build up to an equation that would open up a new possibility that since pressure is force over area, and force is somehow this relationship in three-dimensional space for n number of molecules that have a variety of speeds. So we talk about root mean square speed rather than one specific velocity. Then we would build up to this concept where pressure is going to equal this, but wait, we'll simplify it more. Since pressure times volume equals nkt, which is nRT in chemistry land, but in physics land, we say nkt. If we plug in nkt here, then we can cancel out a bunch of n's and we can come up with this ultimate relationship, which is 1/2 mv squared equals 3/2 kt. And this is the relationship between kinetic energy and the velocity of particles and the temperature. And this makes sense at the extremes. We say that at 0 Kelvin, all motion stops, and this equation is consistent with that concept. And we have this tool, if it's ever useful for us, to figure out how fast a particle is moving. We could figure that out using this equation. Multiply both sides of the equation by 2, 3 kt, mv squared equals 3 kt. So 3 kt divided by m equals v squared. So v equals the square root of 3 kt divided by m. Oh, hey, it's on the next slide. Anyway, so here air is just a mixture of nitrogen and oxygen. and some carbon dioxide and some other things. But anyways, if air behaves as an ideal gas, we could determine the speed of the nitrogen and oxygen molecules when the temperature of the air is 293 K. And what's weird is that it's wicked fast, 511 meters per second. That's the root mean squared speed. So it's kind of like the average speed of a molecule. The average molecule of a gas at room temperature is moving really fast. I don't know if like somebody walks in the room wearing perfume or cologne and you like smell it immediately. It takes a really long path to get to you because it's bouncing off all sorts of other molecules and the walls and stuff, but those odor molecules get to you pretty quickly, even if they take a long path because they are moving so fast. And so this ultimately gives us a tool for saying, okay, if any gas molecule has a certain amount of energy just because it's at some temperature, then I can talk about 12 gas molecules has a total energy of 3/2 kT. So N is just the number of particles, so that would be 12 in this case. 3/2 Boltzmann's constant is K right now. Later on, it'll have a different value. And T in Kelvin. Oh, getting a phone call. The other version of the equation here works with the old-fashioned gas law that we had from general chemistry. We can use that still. 3/2 nRT. Lowercase n stands for the number of moles, not the specific number of particles. Okay. If you have molecules of a liquid here inside a container, some of those molecules at room temperature will have very high energy. That high energy will allow it to jump from the liquid phase into the gas phase. If it jumps into the gas phase, oh dear. One moment. Sorry about that. And so eventually you reach an equilibrium at any given temperature. On average, some of the molecules are moving quickly. And so in the gas phase, others are condensing back into the liquid phase, but they replenish themselves. So we call this vapor pressure above the surface of a liquid at a given temperature, as long as it's an enclosed container. Okay. And we talked about phase diagrams just a tiny bit. There's nothing you have to worry about with those. Okay, so now chapter 14 material is ultimately dealing with the transfer of heat. So earlier on, when we defined heat, Q, capital Q, as the energy that is transferred between two objects, so long as they're in thermal contact and there is a temperature difference. That temperature difference is a key thing. When there's a temperature difference, heat will travel between two objects that are in thermal contact. Now we're talking about the mechanisms of heat transfer. And one of the mechanisms of heat transfer, we don't have an equation to go with this, so this is kind of a conceptual thing. Convection, maybe you've heard of convection ovens or convection heating, that kind of thing. You've maybe heard the term. The idea with convection is that it's not the heat itself that is being transferred so much as the bulk flow of molecules from one place to another. So if you're boiling a pot of water, it is full of what? Tap water, so cold water. You put it on the heating element, and the water molecules that are at the bottom will heat up first. When things heat up, they become less dense. When they become less dense in a fluid, the buoyant force, that kind of stuff from chapter 11, the less dense stuff rises, the more dense stuff sinks. That stuff heats up, rises, sinks, and eventually you have even heating throughout your pot of water. You never put on a pot of water to boil and the water at the very bottom is boiling and the water at the top is still at room temperature. It all mixes together. Typically in a home, you will find a home, a dwelling, an apartment, wherever, that there is baseboard heating, either baseboard electric or maybe baseboard forced hot water. There's heating elements down at the floor level. Why? Because it's going to heat up the air molecules right around it. The less dense air will rise, the cold air will sink, and you'll get even heating throughout the room. I didn't realize how appropriate this would be for an example when I lived with it, but when my wife and I first moved to Salem, Massachusetts, we lived in a condominium unit on Lafayette Street. That condominium unit featured ceiling electric heat. I've never seen it before. I've never seen it since. It is the dumbest thing ever. Ceiling electric heat, there were heating elements that ran in our ceiling. So when we turned on the heat on the wall, the ceiling got hot. So my wife had been to Africa in her college years and had actually contracted malaria while she was there. And she said the feeling that she had in our condo was similar to the feeling she had when she had malaria. Her feet were cold and she had a fever. That's what it was like, because the ceiling was hot, but nothing's compelling the hot air molecules up at the ceiling to come down and warm us up sitting on the floor. Maybe a ceiling fan would have worked in there, I don't know, but it was just a bad idea. It was going against basic physics. Don't try to defy physics. So here's the example of a hot water baseboard heating unit. Heats the air molecules, they rise, cold air molecules come in. We have over the years gone from a refrigerator where the freezer's on the top and the refrigerator part's on the bottom to the other way around. And that's how a lot of refrigerators are designed now, with the freezer on the bottom. Why? Because it makes more sense with convection. The cold air sinks and the warmer air rises. And so it's just a good idea to have your freezer on the bottom and your refrigerator part on the top. This happens, you know, I don't know whoever flies a glider around, but ground, pavement, and green grass absorb heat. It is that heat, that connection between the air molecules and the hot grass or the hot pavement, that causes the air molecules there to warm up and rise. And so you get this mixing of air due to that. We have forced convection in our automobiles to keep our engines from overheating. And there's that. That's convection. There's no equation, there's no math, just a concept. Conduction, we do have an equation and some math. But first, to just give you the idea, conduction is when heat actually goes straight through a material. Typically, if you're cooking, you have metal pots and pans. Why? Because you want heat to go from the heating element through the pan into the food you're trying to cook. If you are trying to, you know, flip something over or something, you generally have a wooden handle or a plastic handle because you don't want the heat to travel into your hand. That would hurt. I guess your pots and pans tend to have plastic handles as well. So things where heat travels through the material very effectively are called thermal conductors. Things that are bad at conducting heat are then insulators, thermal insulators. So this is meant to convey a couple of ideas for the equations that follow. We have a metal rod that is jammed between two different temperature regions. The metal rod is of a certain length. It has a cross-sectional area, and there's two different temperatures. So there's that. So we would find that the amount of heat, Q, that flows through the rod would increase if the cross-sectional area of the pipe or the tube or the metal rod is thicker. It would increase if there's more of a temperature difference. You get that idea. If it's, you know, you're trying to keep your house at 70 degrees, but it's, you know, 60 degrees outside, it's not a huge amount of heat loss through your windows and doors. But if you keep your house at 70 degrees and it's 0 degrees outside, the heat's traveling out of your house faster. It increases proportionally to the temperature differences from one end to the other. It increases steadily with time. So the amount of heat that flows through a material will flow through the material more the longer this is taking place. And then it decreases with the length of the rod. So the longer the rod, the less heat will travel through it. If you have really short thing, very thin windows or something, thin thickness of the glass, more heat will flow, where if it's thicker glass, less heat will flow. So this is just another image depicting this concept, which gives us an equation. Now, every type of material is a little bit different in how well it conducts heat, or on the other end, insulates from heat flow. The value that we assign to it is called the thermal conductivity constant. And the bad news is that the thermal conductivity constant is symbolized with the letter K, a lowercase k, which is also the thing we use for Boltzmann's constant. Typically, if I give you a problem that involves thermal conductivity, I would say in parentheses, K equals 400 for this material. And you would note that in that equation, K is standing for thermal conductivity and you have a number to use. On other problems, if we're using the ideal gas law and it's PV equals NKT, in that instance, you know that K stands for Boltzmann's constant, 1.38 times 10 to the negative 23rd. So you'll know to use that value instead. Now, oftentimes when we're using this equation, what the question is really asking is for rate of heat flow. Rate of heat flow, we're going to divide both sides of the equation by time. And we're going to say Q over T, which is joules per second. So that's a rate of heat flow. That's also watts or power, is K A delta T, capital T, temperature, divided by the length. So if you encounter a question that says, what's the rate of heat loss through a 1 meter squared window, blah, 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 make sure you take this equation, divide both sides of the equation by time, and that's the rate, Q over T. Whereas if they say how much heat is lost in a given amount of time, then Q is in joules, and you have that all set. So some thermal conductivity constants. Metals are good electrical conductors. They're also good thermal conductors. So metals have big numbers, and gases tend to have small numbers and then other things. So I guess they include a goose down, thinking of like a down jacket that you might wear, puffy jacket in the wintertime. Goose down itself has a pretty low thermal conductivity constant, which means it's a good insulator. And then what goose down or just dressing in layers is supposed to do is trap in pockets of air. Air is a good insulator as well. Another thing that's not covered here, but another good insulator is vacuum. If you can eliminate airflow by eliminating the air, then vacuum is a really good thermal insulator as well. So if you see insulating materials in construction, sometimes you see the fiberglass, the pink stuff, that's meant to keep pockets of air trapped so that heat doesn't flow as readily. Sometimes you see the kind of the squishy board, the styrofoam kind of insulating stuff, and that is also meant to keep air from, well, keeps the air trapped, but it's not very dense, and it's a good insulator. And there's the equation again. I have the equations twice. I took a couple of different PowerPoints and mushed them together for this. So if we were doing, a rate of heat loss, we would say that rate is Q over T, Q over T is Ka delta T over L. So Q over T for glass would be glass 0.84, 0.84 watts meter Kelvin times the area, 1 meter squared, times the change in temperature. So outside is 0, inside is 21, so negative 21. Doesn't matter if it's degrees Celsius or Kelvin because the degree size is the same. Divided by length, we want all the units to match. So here it says 0.5 centimeters. We need to convert that to meters. So 0.5 times 10 to the negative second meters. And then we run the numbers and we have a rate of heat loss through a glass window with those temperatures. A rate of heat loss in watts, joules per second is watts. And other examples. Okay. So here near the ocean, we can appreciate convection. The ocean itself tends to reflect solar radiation. The land tends to absorb solar radiation, especially parking lots or green grass. So those absorb solar radiation and heat up. The hot air rises and we get to experience a cool sea breeze coming in from the ocean. Whereas later in the evening, heat that is lost from the ocean or from other places is escaping as infrared radiation, but heat is escaping and we get the breeze is going to come from the land side, which is a little bit warmer. Okay. So here's the world of radiation. We have one kind of intimidating equation that we're going to use with this, but the basic concept is that everything that is above absolute zero is emitting radiation. It is distributing heat into its environment. If you ever see those TV shows or movies where you're looking for a person and you're using an infrared sensor, you see like the outline of the person in red, because the person is at body temperature in a room that is far cooler than body temperature. And so, you see that infrared radiation being emitted. Things that emit radiation also absorb radiation pretty well. There's a unit for that. It's called the emissivity of an object. So things that are reflective don't absorb or emit radiation very well, have an emissivity near zero. Things that are absorbing a lot of radiation will also emit that radiation that has an emissivity closer to 1. The amount of radiated energy is proportional to the surface area and also to the 4th power of the temperature in Kelvin. Do make sure you convert your temperatures to Kelvin for today's quiz and for everything that we're doing and for the exam. So many people get incorrect answers because they forget to convert into Kelvin. So don't forget that. And then the 4th power in Kelvin, so room temperature is like 300 Kelvin. 300 to the 4th power is a huge number, scientific notation. 8.1 times 10 to the 9th. So you're going to see some huge numbers when you're doing this. The idea with emissivity, if you've ever had or seen or experienced a white car parked in the middle of a sunny parking lot, it doesn't get as hot as that black car that is parked in a sunny parking lot. Black, flat, black matted surfaces that aren't reflecting will absorb solar radiation and emit it, and so it feels really hot. Whereas something that's reflective, mirror kind of stuff, that doesn't get as hot. So the equation here is the Stefan-Boltzmann law, and so we have a different Boltzmann constant. This is the Stefan-Boltzmann constant. Sigma 5.67 times 10 to the 8th watts meter squared times Kelvin to the 4th power. Just a constant that goes into the equation here. The epsilon here is the emissivity between 0 and 1. If it was 0, then this would be 0, so that's boring. So it'll probably be 1. Maybe I'll give you a different value. Area, and then temperature to the 4th power. And what we'd be determining is the rate of radiative heat loss for an object with these properties. Yep. Convection requires the bulk flow of matter, of water or a gas or something to be moving around. Conduction is the heat that's actually moving through an object. Radiation doesn't require the bulk flow of matter or a material. So the way that the Earth loses heat into space, once we leave the Earth's atmosphere, it's vacuum. So it can't be conduction and it can't be convection. It can only lose heat through radiation. The Earth will gain heat through solar radiation, which is a range of wavelengths, but includes, visible light and ultraviolet light. And then we tend to lose our heat by way of infrared radiation. And infrared radiation does get absorbed by certain molecules over other molecules, and carbon dioxide is such a molecule that will absorb infrared radiation and keep the heat trapped in the Earth's atmosphere. Just this equation again, and that will take us to the application of all these ideas. If you've ever had a thermos to put your hot coffee in, or if you've ever seen one for sale, maybe in the camping gear area of a store, go ahead and take a look at it. If you take the top off and look inside, you see that it's a mirrored surface on the inside usually. So there's a stopper on top that prevents the air molecules from taking heat out of the situation, preventing heat loss by convection. It is also made out of materials that are not good conductors. Even if the thermos bottle itself is metal, you will find that there's a layer of insulation between the metal and the inside, which makes it so that heat isn't lost by conduction, conducting straight through the material. And then on the very inside, if you look inside, you'll see that it's a reflective material. The reflective material prevents heat loss by radiation. So it's all just kind of bouncing around back and forth in and of itself. So that's how your hot soup or hot coffee stays hot inside your thermos bottle. Okay, there's some other things that I have in this PowerPoint that we will cover another time, but I don't want to overwhelm you, and this stuff is coming up next time. So that was faster than it went this morning. I guess that's what happens when you lecture on the same material twice in a day. So I will post the recording of this lecture. But now I want to give you a chance to ask any questions you might have from the Chapter 13 homework, because we have a quiz on Chapter 13 material. Let me scroll down to the Chapter 13 stuff. So just to kind of prep you, if two things are in thermal equilibrium, we say the two systems are at the same temperature. If they're not at the same temperature, then heat will flow from one to the other. And if heat is flowing, then it's not in thermal equilibrium. If you want to get a metal peg to fit inside a hole, you would heat up the part of the system that has the hole and then put the cool peg in there. And then when the rest of the thing cools down, it'll form a nice tight seal. I get this almost every morning. We have coconut oil inside a glass jar with a metal cap, and sometimes the cap is really snug and I can't get it to twist off, and then I run it under hot water. The metal absorbs the heat very effectively and expands, and then it doesn't have as tight a seal and I can take the lid off. Impressing you with how big a mole is, some conversions, Fahrenheit, Celsius, Kelvin. The Eiffel Tower gets taller. If the temperature goes up, we're using that delta L equals Ka delta T. Here, let me, I think I have another window open. Let me just share screen 2. This will go easier. So delta L equals alpha L naught times the change in temperature. On the quiz itself, I do give you R and Avogadro's number, and then I was cute and I just said that Boltzmann's constant is R divided by Avogadro's number. So you can do the math there. It's 1.38 times 10 to the negative 23rd, but you might have that bit of math to do. I give you the conversions from Fahrenheit to Celsius. All right, so I'm doing the blah, blah, blah routine, wondering if anybody has any questions from chapter 13 homework before you take the quiz. And I'm not seeing any questions in chat. So that's indicating that you don't have any. So if that's the truth, I will encourage you to go ahead and take the quiz. The quiz is a little bit on the long side. I don't know, just they're pretty straightforward questions. So I asked a couple more, I guess, but your numbers are different than mine. Don't copy my numbers. Here's the equation sheet if you just need it to look at. I'm here on Zoom chat if you have any questions. Have fun, good luck, do well. I will post the video of our lecture as soon as it finishes processing. And